Hey everyone, today we're looking at the work done on charges by electric fields. We did some demonstrations in class to try and illustrate if potential energy of a charge will increase, decrease, or stay the same based on moving charges from one location to the next. So the example we tried was taking a test charge, a positive, and moving it from infinity all the way to some location here. We call that point P. And remember, since the thing that is doing work here is the work against the electric field or with the electric field, that's a conservative force. So it doesn't matter the path that I take from point A to point B, I just have to go from one location to the other. Now remember that the positive charge has an electric field that points away in all directions. And since it's a point charge, we know that the field strength gets weaker and weaker the further out we are. So as I start walking from infinity, it's very easy to move that charge from infinity towards point P, but as I get closer and closer to that charge, the force is going to grow by 1 over r squared, and it's going to be very, very hard to fight that. When I do this, we can say that the field is applying a force backwards, and I am applying a force forwards. The displacement of charge is going to be from infinity to point P. So if you look at the work I'm going to do to move that charge, it's going to be positive work. But if you look at the work done by the field, because that's really what matters, the work done by the field is going to be negative work, because the force field is going to push away and the charge is moving against the field, which means that my overall potential energy is going to increase. Where's that energy coming from? That energy is coming from me doing the work and pushing that charge towards the other charge. If I was going to actually calculate the work done is force.dr. The force between two charges is just kqq over r squared. And since the work is being done by a conservative force, we're going to have to integrate the force dotted with displacement. So we put in what the electric force is. We're going to get k q1 q2 over r squared dr. And we're going to have to integrate that from infinity to point P, any location that I end up close to the charge. If we pull out our constants here, the constants we've got are the negative kqq, and what's left behind is a 1 over r squared dr. So when we do this, we get negative kqq, integrate 1 over r squared dr. Well, integrating 1 over r squared gives us negative 1 over r. And remember, we have to evaluate that between our two bounds. So we're going to evaluate that from infinity to point P. Well, when we put infinity in here, 1 over infinity is pretty much 0, and so all we need is location 2, which is point P. And when we do that, we get a negative 1 over r multiplied by kqq. Our electric potential energy is kqq over r. So it's a 1 over r relationship to solve for the potential energy between two charges. Remember, energy is scalar, so it can be positive, negative, or 0 depending on what charges are. However, there is no direction you have to worry about. Potential energy, you just put in the charges, do not do absolute values, actually put in the real positive or negative sign for the charge to see if you're dealing with negative energy or positive energy based on your setup. So at the bottom of the worksheet we did in class today, there are two example problems. One is an alpha particle fired at 1 million meters per second towards a bead that is charged at -1 nanocoulombs. The question is, what is the speed of impact? If you don't know what an alpha particle is just a helium atom that is stripped of its electrons, so it's a +2 charge. But I'll do the example down below. The electron being fired at the same bead, and it reflects at a turning point of 0.1 millimeters away from the surface of the bead. How do we figure out what initial velocity we had to make that electron try and get close to this negatively charged bead? So let's set up the problem. So here we go. We got the electron. We want to know how fast do we have to shoot it so that it can get all the way to here and come to a stop. Distance of is going to be 0.1 millimeters from the surface of the bead. Remember that the bead itself is 2 millimeters wide, so that's going to come into play a little bit later. So what you can do for this is set up a conservation of energy problem for yourself. You want to think about what energies you have in the beginning and what energies you might have at the end. So in terms of energy here, I could say that, well, it's going to be moving, so it's going to have kinetic energy. If I want to say it's got potential energy, not really any potential energy, because we could say this bead is really far away, close to infinity, so there is zero electric potential energy. But when we get all the way over here, we've got a point where our velocity goes to zero, that turning point. So when we get to the turning point, the charges stop moving. So the kinetic energy has run out, which means there must be electric potential energy there. So if that's the case, what we can say is that all the kinetic energy turns into electric potential energy. And the goal is to find that initial speed. So let's set that up. Kinetic energy for charges is no different than anything we've ever done before. It's 1/2 mv squared. Over here, the potential energy is going to be K charge 1, charge 2, all over r, just the r distance. Don't square it. If you square it, you get a force, not energy. The goal is to find the initial velocity, so we can rearrange this very easily. I can multiply the 2 over and do q1, q2 all over the distance, and I want to get rid of that mass, so I'm going to divide the mass over, and to solve for velocity in the end, we need to take the square root. So the square root of 2kqq over mr is what we need to do to find the initial velocity. Now remember that the one charge is the electron, that's 1.6 to the negative 19, and this is the 1 nanocoulomb. The mass that you have down here is the mass of an electron. That's a given. That's something you can go find on your equation sheet. That's negative 911 to negative 31st kilograms. And the r distance. The r distance is how far we are from center to center. So how far from the center of the electron to the center of the bead. Well, it looks like it's about 1.1 millimeters. So if you put all that in and solve for velocity, what you should end up getting is a speed of around 5.36 times 10 to the 7th meters per second. So it's a really fast speed. We're talking about 53 million meters per second just to get an electron to get within 1/10 of a millimeter of that charged bead. And if you want to know if that's legal, remember it's got to be less than the speed of light. So really this is only 18% the speed of light. So it definitely can go that fast. It's definitely not a problem. Try the other example for the alpha particle, see what you get for your speed of impact, and we can compare our answers in class. The last thing I want to focus on here is the charges in uniform electric fields. All the examples we did today were for charges moving towards another point charge. But what happens when we're in a uniform field? Well, like when we're in a uniform gravity field, the force doesn't change based on where you are. I just see that the field is pointing to the right. So if I want to know why the field's pointing to the right, there must be some, again, large positive charge over here and some large source of negative charge over here, maybe 2 plates that we just can't see the edges. So we're going to put a charge in that field, and we want to know the work done by the field. If we want to find the work done by a constant field, we can do our same setup we did before. So du is the negative integral force dot dr. This time the electric force is coming from the electric field, and since it's a steady field, we can just go with the definition of electric field being force per charge. So really, if I want to solve for force, I can put that in here and get negative EQ dotted with the displacement. That means I'm going to integrate from any 2 locations that I pick in there, so from point A to point B, and du will just become my change in energy. So if you look, I pulled the electric field out because it's uniform, I pulled the charge out because it's just the charge that's in that field, and dr just becomes change in r from one location to the next. So it's really a displacement. So my change in potential energy here is negative EQ times the displacement, how far you've moved in the field. Now remember, to have energy change in a field, you have to move with the field. If you move perpendicular, you don't get any energy loss whatsoever. Why is it negative? It's negative if we have the example like we have right here. The charge is moving to the right, the field is to the right. The field is doing positive work, so we're going to lose potential energy. If we reverse this and put a positive charge and launched it this way with some initial velocity, then we'd be fighting against the field, and technically my displacement would be in the negative direction. So if I go back to my formula, put a negative displacement here, what I'll end up getting is a positive increase in change in potential. So you could do the same conservation of energy like we did for the last example for the electron bouncing if you have something in a uniform field. This charge would slow down on its way towards the positive plate, it would eventually stop and then head back. So you could do all the kinematics and energy conservation you'd like to solve for speed or distances from each of the plates or whatever you might want to look for in there. But again, you move that charge from this location over here, no work has been done. That's like carrying a book across the room. The force and the displacement are at 90 degrees to each other. When you have 90 degrees for work done, you get 0.